Okay, good afternoon. I'm Jin-Gyu from Center for Disruptive Photonic Technologies at NTU in Singapore. And today I'm going to talk about our recent efforts toward the control of light emission from quantum emitters. And for that, we will be putting those emitters in an environment where the refractive index is close to zero. And we will see how the emission rate is affected by such a medium, and especially in a one-dimensional Epsilon-near-zero waveguide today. So if you put such light emitters in such a medium with vanishing refractive index, would you observe a suppressed emission because you have negligible index or negligible number of optical modes? Or would you observe an enhancement of light emission instead? And we want to answer this question by looking at how the photoluminescence from quantum dots is changing when you put them into the core of a one-dimensional ENZ waveguide like this. So we will be talking about materials showing near zero index. And you can achieve this by having near zero permittivity or near zero permeability, or both the permittivity and permeability at the same time. And you can find some materials around you which naturally show index near zero by having zero crossing of the real part of the epsilon at UV or infrared part of the spectrum, with fairly small imaginary part of the epsilon at the same time. So for example, this topological insulator or wideband gap semiconductor in the UV regime shows epsilon near zero around 200 nanometers over here with small imaginary part of the epsilon. And transparent conducting oxides are known to have zero crossing of at the near infrared part of the spectrum. Or you can rely on polaritonic materials to access the mid-infrared part of the spectrum as well. So you can get index near zero response from materials already existing in nature. And if you want a little bit of tuning capability, you can engineer the materials by doping or changing the compositional ratio of the materials. Or you can instead design a media with index near zero by structuring materials. So you can create epsilon near zero response from wire array, which is also known as plasmonic metamaterials, or you can get the ENZ response by stacking positive and negative permittivity materials like this. Or you can design a photonic crystal with a direct cone with accidental degeneracy. Then you can create a 3D, 2D, or one-dimensional near-zero index media. Or you can simply scale down the RF waveguide to the nanoscale. Then the scaled-down version of this waveguide will show near-zero behavior at this cutoff frequency. So you can get this near-zero response in the spectral region of your interest, either by having a natural media or a structured media. And with these material systems at hand, now you can manipulate the light emission without phase advance along the ANG channel, or you can match the phase of nonlinear process in a nonlinear crystal, or you can aim to achieve the circuit analog in the optical frequencies by having the ENZ media as the background material. Or you can control the light emission itself from quantum emitters. And naturally extending the idea of equal phase between emitters, you should be able to accelerate super radiance, or you can achieve a entangled photon source from these material systems as well. And let's get back to the question that what will happen to the emission rate when you put emitters in near zero media? And the number of optical modes will be negligible, so will you see suppression of light emission around near zero frequency? And based on this nice piece of theoretical work, it might be true for three-dimensional and two-dimensional index near zero media, but for one-dimensional ENZ media, it is expected to have a huge enhancement in spontaneous emission rate at the ENZ point due to the strong enhancement of the impedance or emitter to ENZ mode coupling. And there has been a demonstration on how the radiation pattern from quantum emitters can be affected by embedding them inside such a media. But it has not been clear how the emission rate would be affected by the presence of this near-zero media. And we aim to demonstrate the luminescence enhancement in one-dimensional ENZ media. And to achieve one-dimensional ENZ media or waveguide, you can take two approaches. One way is to design a photonic crystal waveguide, and the other way is to use a cutoff behavior in the RF waveguide. And we will use this optical frequency version of this RF waveguide by scaling the dimensions, mainly the width of the waveguide, to tune the cutoff frequency. And here you see how the effective index changes as a function of the waveguide width of 100 nanometer thick waveguide. And the effective index here was obtained from the propagation constant of the fundamental TE mode of a 100 nanometer thick waveguides, assuming silver sidewalls and PMMA cladding. And by tuning the width of the waveguide from 100 to 180 nanometers, you can achieve index near zero somewhere in the visible part of the spectrum. And we worked with a cadmium selenide and zinc sulfide core shell quantum dots with a central emission around 630 nanometers. And having a core shell quantum dot was important in terms of photostability and fabrication as well. And to achieve the waveguide thickness of around 100 nanometers, we play with the density of PMMA and quantum dot mixture and the spin speed during the spin coating. And this shows the cross-section of a completed multi-layer film of silver, PMMA and quantum dot layer, and another silver layer on top. Then we define the sidewall of the waveguide by milling the film with a focused ion beam. Here you can see the side of the cladding is exposed, and we need to cover it with another layer of metals. So after additional silver coating on the side, now you can define the length of the waveguide with additional focused ion beam milling. And here you can clearly see that the core of a 100 nanometer wide and 100 nanometer thick waveguide is nicely formed. But to characterize the optical performance of this device, you need to couple light in and out of these tiny waveguides, and that's why we constructed these two 45-degree mirrors here and here. So the light is coupled into the device by one of the mirrors here and here, and the emitted light from the quantum dots inside the waveguide will be outcoupled by both mirrors. And to precisely pick up the light emission only from the waveguide, we used a scanning confocal optical microscope. And here is an example of a photoluminescence intensity map at wavelengths between 550 and 750 nanometers. So you move your excitation beam and measure the collected photons to construct this kind of map. And here you can clearly see two bright spots over here and here. And this is when your excitation beam is hitting the 45-degree mirrors, whose positions are highlighted over here. And to measure the PL spectra from quantum dots in the waveguide, we fixed the position of 4 or 5 nanometer excitation laser on one of the mirrors and measured the luminescence. And in a control waveguide, which is shown here, there's no sidewall, and it means you don't have any cutoff near the quantum dot emission wavelengths. So that's what you can see here. Here you're looking at how the PL spectrum changes while you change the width of the quantum dot embedded control waveguides. And there's only a gradual increase of the photoluminescence intensity, as you increase the width of the waveguide. And this is straightforward to understand since the volume and the number of the embedded quantum dots will increase as you increase the width of the waveguide. But here, if you work with a waveguide where the sidewalls are completely covered by silver films, you will see only a muted response from the waveguide until you hit the width of 160 nanometers, where you see a pronounced peak over here. And we attribute it to the encounter of the ENZ point of the waveguide and the emission wavelengths of the quantum dots. So we have shown that light emission from quantum dots or quantum emitters in general can be enhanced by putting them in the one-dimensional ENZ waveguide, as predicted by the theoretical study mentioned earlier. And as a next step, we are studying the temporal and quantum aspect of the light emission from the emitters in one-dimensional ENZ waveguide. So here is the photoluminescence decay curves of quantum dots, whether they are embedded in a waveguide or just sitting on a glass slide. So from this measurement, we have seen a factor of 40 enhancement of the emission rate, but the measured lifetime was limited by the instrument response as we used a TCSPC and an APD. So we couldn't resolve it beyond a 300 picosecond. And we expect to get a better temporal resolution by using a strict camera instead. And also we are doing some second order correlation measurement to check the collective behavior from the quantum dots embedded in the waveguides. In conclusion, we have demonstrated the first observation of enhancement of quantum dot luminescence in ENZ media at the waveguide cutoff, and we hope to see how the temporal and collective behavior of quantum dots can be affected in such media. Thank you.